Welcome back. In this video, we will be discussing the foundations of scientific numbers, significant figures, and scientific notation. Sig figs, or significant figures, indicate the precision of measurements. Sig figs allow us to account for the uncertainty when measuring volumes in graduated cylinders, masses with analytical balances, and lengths using meter sticks. The reason significant figures are important is that we cannot be more precise in our measurements than the scale of our instrument. For example, if you're measuring a volume of water in a graduated cylinder, you may be between two markings. Is this volume drawn an 8 or a 9? In reality, it is between the two, and we are uncertain to the true volume. Sig figs allow us to know the limits of our measurements. Here are the rules for counting the number of significant figures in a measured value. Rule 1, any non-zero digit in a measurement is significant. So in the example, 11,325 meters, we are going to have 5 significant digits, one for each one of our values. Rule 2, zeros between non-zero digits are considered significant. We commonly call this the trapped zero rule. An example of this would be 7,003. The 7 is significant, the 3 is significant. So the two zeros that are trapped in between are going to be considered significant, giving us a total of 4 significant figures. Rule 3 is typically called the left zero rule. Zeros to the left of the first non-zero digit are considered insignificant. This occurs frequently for very small measurements in units. An example of this would be 0.00342 liters. This measurement has 3 significant figures because the 3 zeros to the left are insignificant and merely placeholders. Rule 4 is commonly called the right zero rule. Zeros to the right of the non-zero digits are considered significant only when the number contains a decimal point. For example, 400 grams. How many of these digits are significant? The only digit that we are really sure of is the 4, coming from the first rule. But what about the 2 zeros? Because there is not a decimal point, they are not significant, so there is only one sig fig. What happens if we add a decimal point? Now we have 3 sig figs, because we have made those 2 zeros significant. You can see how this case can be ambiguous. We can avoid this problem using scientific notation. Scientific notation allows scientists to make their numbers easy to read and interpret. One of the biggest benefits is that it allows us to know exactly the number of significant figures that we're dealing with. Let's go back to our previous example of 400. We are only sure about one significant digit. How can we indicate if there are 2 significant figures in our measurement? The form of the numbers needs to be written in scientific notation as n times 10 to the power of m. N is a number going to be between 1.0000 and so on, and between our 9.9999 and so on. Well, the m is going to be the exponential power of 10. For every decimal place we are going to move left or right, we're going to change the value of m. So for our 400, if we would like 2 significant digits, we know that we are going to have to manipulate the power of 10. All of the digits in n are going to be significant, while m is never significant. To accomplish this, we are going to have to move the decimal place 2 places to the left. And if we do that, our value for m is now going to be 2. Notice that this is still 400, just written as 4.0 times 10 to the second, and 10 to the second is 100. A good rule of thumb when moving the decimal place to the left is that you'll increase the value of m. But if you're moving the decimal point to the right, you're going to decrease your value of m. Let's return to our example of our 0.00342 liters. If we move the decimal place 3 spots to the right, we're going to produce a good value of n. Seeing that we have moved the decimal place 3 places to the right, our value of m is going to be -3, giving us a result of 3.42 times 10 to the -3rd liters. Notice that this measurement still retains the 3 sig figs. Now that we have our rules for significant figures, and we can use scientific notation to help us out with our number reporting, we have to be careful not to create digits when doing calculations. Many students will punch numbers into their calculators and report all of the digits on the display. Most of the time, many of those digits are insignificant. Let's look at the calculations such as 42.3 centimeters times 8.22 centimeters. If we do this calculation for area, we need to report the result with the correct number of sig figs. But what's the correct number? When you put this equation into your calculator, you will get a value of 347.706 centimeters squared. Both original values have 3 sig figs. So how many should my answer have? When doing multiplication and division, you must use the fewest number of significant figures from your original data. In this case, both have 3 digits. So our reported answer should be reported with 3 digits as well, giving us the answer of 348 centimeters squared. All of those decimals are artificially created by the calculator and should be rounded. Let's look at another example where 2 values have different numbers of sig figs. 657 centimeters cubed divided by 8.459 centimeters. Our numerator has 3 sig figs, while our denominator has 4. The calculator displays the answer as 77.669755. But we cannot report that number. We will report 3 sig figs because we are only allowed as many sig figs as our least of our measured values. When limited by sig figs, rounding rules must be applied. If the first digit that is insignificant is between 0 and 4, we are going to have to round down. A case of that would be 44.23 grams. But if we're only allowed 3 sig figs, this being the last significant digit, we will remove the 3 and only be allowed to report 44.2 grams. If the first insignificant digit is between 5 and 9, we will have to round the last sig fig up. When we needed 3 sig figs, you will notice that the first 6 here is going to be our significant digit. We are going to round the 6 up, thus turning it into a 7, and the answer we're going to report is 77.7 centimeters squared. Now let's do an example with addition. We have 8.943 meters plus 15.784 meters. Looking at the measured values, we can see that the first value will have 4 significant figures, while the second has 5. The rule for addition and subtraction is not the same as multiplication and division. The rule you will use is commonly called the last common place rule. This means our last significant digit will be the rightmost place of the value that is common in both original terms. In the addition example, both numbers have a common decimal place up to our third digit, typically what we call the thousandth place. So when we do the addition, we will report an answer to that place, giving us 24.727 meters. This answer has 5 significant digits, which is allowed under the addition and subtraction rules. Now let's try a subtraction problem. This time we will write it vertically. 7.235 liters minus 2.4 liters. Using the same rules that we just established, the last common decimal place is going to be our first decimal place, or the tenths place. When lining this up vertically, it is much more obvious for us to see. So if we do the math, we cannot report the 4.835 liters that we would get from the calculator. We are only allowed to report the 4.8 using our significant digit rules. In our previous video, we discussed logarithms. These functions have special significant figure rules. In our term, anti-log term of e to the 3.24, we actually have 2 different types of terms. The numbers to the left of our decimal place are commonly called the characteristic and are not significant, while the numbers to the right of our decimal place in our exponent, commonly called the mantissa, are significant. In this example, we will report 2 significant figures, giving us the answer of 26.